So welcome to the 7th, I think, MFANS technical meeting. Last time we went over data viz in Python, in which the real friends we made along the way was learning that you should always do data viz in R instead. So today we're going to be going over some modeling in Python instead, and the advantages between R and Python in terms of modeling. At a low level, like if you're just doing linear regression, basic linear and logistic regressions or things of that nature, there's not too much difference between the two. But if you do get to higher level modeling techniques, if you're doing anything related to machine learning or any crazy, funky, fresh models, you will have to use Python. R is limited in that sense. So it's important to know, be familiar generally with how you make models in Python, especially if you're doing any machine learning, which to my knowledge is just a bunch of logistic regressions, but that's besides the point. So we'll get started right away. Here, if I can find it, share my screen. Yeah. Okay. Yeah. There we go. So it looks like you guys can see everything. That's fine. So here is the. Okay. So I did a little pre-work this time. I'm gonna drop everything in the chat, and I'll explain kind of as we go. So. Shit. So just to. And you guys can see this, right? Okay. Sick. Okay, so what's going on here? Well, this first one, per usual, we are just importing the packages that we need. So pandas for the data science, NumPy for numbers things, pre-processing, we actually don't need that guy. Matplotlib for any sort of data viz stuff that we might want to do really quickly. And I guess we'll import Seaborn while we're at it. This is SciKit, that's what SK stands for, learn. This is where all the modeling stuff you want, generally speaking, is, besides machine learning shenanigans. And linear model. So linear models is just a class of models. We did a linear model last time in R. We're going to do a linear model here in Python today, just because that's the easiest to kind of understand. And you should be familiar with that in your science classes. And if you've taken a physics class, linearizing data is big. So this is just a class of models where it really boils down to you have some data and you want to fit a straight line to it. Logistic regression is included in this. It's just a special line. And from that, we will import. So this import word, I don't think we've seen it before. So we have some large packet SciKitLearn. And SciKitLearn is massive. It's up several gigabytes worth of functions, and we don't want to load all of that in. We only want to import a very specific part of it. So of this whole thing, so of all of SciKitLearn, we just want to put in the linear model, and just from that linear model, we want to import their linear regression. And the same thing here, model selection. This is a class of this is not a class, a group of functions which you use to pick a best model or to do some best practices with models. For example, and here we're going to import a function which lets us split data into a training set and a testing set, which is, of course, extremely important if you don't want to overfit your data. And this is a little different from what we've been doing the past couple of times. We've just been looking at 2020. And now you see here we have an array, or a list rather. In this list, we have several different years. We have 2017 to 2020. And why are we doing this? Well, as we discussed in our R modeling video, meeting, you want as much data as possible when you're building a model, especially with respect to sports. You're building everything off of historical data. So you want as much historical data as is relevant. So we're just going to, so arbitrarily, I picked the last 4 years, including this year. We're going to run with that. And this for loop, this is a very classic Python technique. where you say, okay, I have some item in a list and I want to go through that list. So we're just going to do a for loop on that bad boy. As you can see, we're just reading in the CSV and we just are reading in the string of every entry in here. And if you have taken a computer science class in Java or C++, I believe, this may look odd to you. You would have, usually those you'd have to go to the index, like go through I in 1 to length of this list. But in Python, you can just say, oh, for each element in this list. So we're just going to go through each year and make a string of that and add it to the URL to the CSV that we want. That'll take a moment to run, just to demonstrate. And since of course I'm sharing my screen, it might take a minute longer because I have lots of things open down here, as you can probably see. But while that's going, I guess we'll get started explaining a little bit what's going on down here. So this, we have the disgusting Python chain of functions, as we've alluded to before. This is what it can look like, pretty gross. Also, I would like to remind you guys that for the past couple months, I've been programming almost exclusively in R. So my Python code will look gross and it will be inefficient, and I'm not sorry. Well, I am very sorry, but just a fair warning, you can probably do this in better ways. So what's going on here? So remember the way that Python usually works. You start off with your object, in this case, our data, which is the data frame, which is all the play-by-play data from 2017 to 2020. This includes playoffs, importantly. Not important, it's just, you know. So we start off with our object, data, all the play-by-play information. Then we do something to it. So we're going to group it by each game. And if you want a quick reminder of what the data set looks like, so we have our index, and the game ID is like, it's year, week, away, home. Year, week, away, home. That's what it looks like. That exact order isn't super important, but the fact that this is unique for each game is. Okay, so we're going to group it by each unique game ID. So we have each game. And inside each game, this is a function we haven't seen before, but is extremely useful in R or in Python. It is the apply function. So we're going to do something across the groups. Similar somewhat idea to summarize, but it's a bit clunky. And when I mentioned this is probably not the best way to go about it, this is probably not the best way to go about it. You have to write this lambda term. I'll be honest, I don't know why. On Stack Overflow, it says to do so. And so what we're doing here is, so step by step. So we have our data, we have our play. We're grouping by each game. And then we are applying some function across each group. And we're just for the sake of it, we're going to define that group to be X. So across each group X, we're going to apply some condition on it. If you remember, we have some condition. So in that group X, we will only look at when the possession team column is the same as the home team, or the value in possession team will be the same as the home team. So this is when the home team has the ball. And then we're going to look at the EPA for that play, and we're going to take the mean. So this will give us the EPA per play of the home team in a given game, of the home team's offense. And then we'll take the mean, and then we're going to reset the index so that we can actually have this game ID column as a column and not as the index. So it won't be like negative 0.05 with, instead of 0 as the index, that. So that just helps so we can merge the data later. Spoiler alert. And then if we don't have this, I'll demonstrate this down below. So if we just really, oh here, well, nothing's going to pop up now. But if we just really quick copy and paste this guy right here, and we take out this rename. So we have every game, and we have the home EPA per play, but that's 0. And that we like our variables, we like our columns to be have useful names, and 0 is not a useful name, especially if we want to merge multiple data frames, which that's what we want to do. So just Oh, and so again, it's gross. It's probably not the pretty way to do it. And we just repeat it again for the away team. So if we just look at what we have, so we have the home EPA per play for every game. So the Lions in week 1 had an EPA per play of negative 0.04. And this seems like a strangely low amount of games. Oh, wait. I messed up. So we actually did something wrong in here. So what we're doing here is we're just getting we're telling it to read in data, but then just read over it. So we're just reading, so it reads 2017, saves that, reads 2018, saves that, reads 2019, saves that, but it doesn't actually add the data frames together. So what we want to do is we want to add some data frame df equals pd.dataframe, I believe. And then we want to do df equals pd.concat. This concatenates them. This adds rows together. So df data axis equals 0, I believe. Oh, is it? What's it, data frame? There we go. Okay, so we're just gonna try that again. If I can't get this in 2 minutes, we'll get the okay, so not quite sure I'm messing here. So that we're going to go to our favorite friend, Stack Overflow. How to pandas data frame. Let's dot append, right? Dot append. Yep. So it's df dot append data. Does that work? If this doesn't work, we'll just move along. So since it's taking a while, I assume that means it's working. So basically what's happening is we defined a new empty data frame. There's nothing in there. And then in that data frame, we're just adding stuff onto the end of it. Yeah, see? So here, now we start in 2017. So it's like, okay, so we have the empty data frame, then we add the 2017 data, then we add the 2018 data, then 2019, 2020. That's what we're doing right now. And just to make sure that we do have all that data, I'm just going to change from data to df, because that's the object that we're doing all of these functions on. Okay, and now we're going to merge these together, just so we have them in one concise place. pd.merge home EPA per play and away EPA per play. Should work. And just to make sure. Yeah, see. So in 2017, the Cardinals and Lions had the worst game ever, with the Lions having minus 1.8 EPA per play and the Cardinals besting that with a minus 2.8. That seems, what was the score of that game? Oh, we can actually, I'm glad you asked, actually, because we're going to check that right now. So what I arbitrarily choose for us to predict today is totals. So how we're going to do that is, so to do that, we actually need to know what the totals are for the game. So we need to know what the scores are for the game. So to get the scores for the game, what we're going to do is same idea. We're going to group by the game, but then we're going to make an aggregate. This is similar to summarize. So we're going to get the last So the last home score of the game and the last away score. So this will give us the final score of the game. And if you don't know, totals are, so when you bet the total, you bet how many points are going to be scored in that game. And then we reset the index. I'll put this in the chat. Actually, I'm going to throw this in as well. Yeah, so now, okay, so now of this terrible Cardinals-Lions games, we'll see what this final score was. 35-23. Never would have guessed.
Yeah, I'm surprised. I'm surprised our EPA per player was so low for that game because like we played really well and we had like a blocked punt. The Cardinals blocked a punt and the Cardinals blocked a field goal. So like it should have been more of a blowout actually.
Yeah, that's very interesting. But like here we got when the Rams absolutely destroy the Colts, and yeah, that checks out. And in this game we have, so those are both high, and that's a pretty high scoring game. So that's an oddity. Oh, cool. Okay, so now what if we want to get the total? Well, now we just define a new column. Equals scores, home score, plus scores, away score. And we'll look at it again really quick. So now we have the totals. And just for fun, let's see what the highest scoring game from 2017 to present is. So total.max, 105. Interesting. So let's try and see what that game is actually. And we can do that by doing. So we can do that by looking at the entire scores data frame. So scores, total equals, and then we're going to look at the game ID. So what we're doing here is we're going to look at the scores, and then we're going to filter it when the total score is equal to the max score, and then we're going to look at that game ID. So it was the, oh yeah, that makes sense. The 2018 Rams Chiefs game. That was the Monday night game where they each scored a bajillion points. So cool, fun facts for your next trivia night.
Could you go up to the cell where you get the data? For some reason, I'm still getting 2020. I might have put something in wrong. Yeah, equals PD data frame.
Yeah, I in the chat too.
Oh, okay, thanks.
Yeah. I just need this append right there. Okay, so now what we want to do is we also want to add. So the first thought is we're just going to model the totals by looking at the EPA per play of either team. Just a really rudimentary, simple model. So we'll do this by, and of course, final prep. So we need to merge data frames again. So pd.merge, scores, and EPA per play. And then we can look at final prep just to make sure it is what we want. Yep, and there we go. But first, of course, we want to just make sure that these do have a linear relationship. So what we're going to do is we're going to do some quick data viz. So we're going to look at final prep plot. And we'll just look at a scatter plot. Plot.scatter x equals, look at the total, y equals home EPA per play. So there does look to be a general linear relationship there, nothing too crazy. But what if we actually add the away EPA per play here? Oh wait, I think I need to do a This actually is a callback to our last meeting as to don't do data business. Okay, never mind. Okay, so now let's look at away EPA per play. Okay, so we can see they both have a generally linear relationship with the total, but of course it's not super strong. What might be stronger actually is if we look at the away score and the away EPA per play. That is a much stronger correlation. We can do the same with the home score and the home EPA per play. So these have much stronger correlations. So from here, we can think that if we just do a straight totals, that might not be super good. But if we try and predict home EPA per play and away EPA per play independently, and then add those together, we might actually get a better totals model. That's just something to keep in mind, though. Oh, and of course, we want to check that we don't have any like major collinearities here, because there's several assumptions that go into making a linear model. One of the assumptions is that you can memorize them by line, that one, the data is linearly related. We more or less have that. Two, they're independent. So the outcome of each game is independent of each other. We can comfortably assume that. N is normal, so that each input has a roughly normal distribution. We can check that if you want. And E is, I forget what it stands for, but it means that they're not linearly related. And they are not. There's not really any relationship between the variables you're putting in. And there is not. These are, and if we trick our eyes, maybe we can see some sort of line here, but really there's no significant correlation there. Just to be thorough, we can actually check that our inputs are normally distributed. What is it? Plot. Oh, it's just hist. X equals away EPA. Okay, so it gives us each. Oh wait, but they're on totally different scales. That's super annoying. Here, so here we'll just look at, so to look at each, we can do the so home EPA per play. This will make it a little easier. Okay, so that's so that has a bit of a left tail, but if you look here from -4 to 0.4, it's close enough where we can fudge it. We can say it's roughly normal and move along with it. And we'll look at the away EPA per play. Again, roughly normal. We can work with this. And just look at score, the totals too. Yeah, it's roughly normal. There is I believe this is a right tail, which is a little concerning, that might be something that if we want this to be a really accurate model to worry about, but not too much for these purposes. So just know that any linear model, based on what we're doing, it will probably underpredict these super high scoring games. It won't predict the Chiefs and Rams to each put up 50 points on each other, which is probably fine. I mean, you don't necessarily want your models to predict super outlier outcomes. Okay, so cool. We have what we want. So now what we want to do is we want a training set and we want a testing set. So we actually fit this sucker. So how do we do that? Well, luckily in Python, it is super easy. And you guys can definitely see what's on my screen right now. That's fine. So that's, I'm just gonna say here. There it is. Okay, so how do we do it? Well, it's rather simple. It's just this train test split function. So we go back here. So we train test split. So we can see the inputs here. So it'll split arrays into random training and test sets. So we will throw in our final prep. And then the test size. We have to define some proportion. So we'll just say we want our testing set to be about 20%. Now, just to quickly explain a training set, why do we do this? Because we don't want to overfit our data. Overfitting means we just connect the dots between our points and what we want to predict. And that obviously is not what we want. So here we do a quick little paint. So what overfitting does is if we have these lines, really what we want our model to do is to do something roughly like that. But what overfitting will do is in brown is it will go, okay, I'll give you the function that fits best, and fitting best is actually just connecting the dots. And if we want to predict data off of this, that's really not what we want. We want this good old black line. So by splitting into training and testing sets that we keep separate from each other, it lets us make sure that doesn't happen. How big they are, I don't know the rationale behind any of this. So I just make the testing set 20% the size of the training set. Training set is usually supposed to be bigger, obviously, because you need more data to build it off of. So if we just run this, we are left with, so we're left with two data frames, a training one, the bigger one, and the testing one. So, and how do we get these? So we'll do train test. And if we actually look at, so if we look at train, this has the 758 rows. And if we look at test, we have 190 rows. Good job. Okay, so how do we actually fit this model? So fitting is, of course, making this black line. So how do we make this black line? Well, first we make an object that is a linear regressor. So we'll just call this LR for linreg, for our linear regressor. And it is, here, wait, a little inside baseball. It is, it is just a so to make a linear regression model, it is, or a linear regression object, it's just linear regression. Okay, and so now what we want to do is we want to train this on the training set as the name suggests. So we do train. So we'll have this trained model equals linreg.fit. So we'll do train, and we want to train it on the home EPA per play and the away EPA per play. So home EPA per play and the away EPA per play. And we want to fit it on train total. And if we run that really quick, so now we have our train model, which is a linear regression object. And here I'm just going to, get that afterwards. So, okay, cool. So how do we know if it's good or not? Well, we have a couple ways of doing this. First of all, what we're going to do is we're just going to look at the R squared. So how do we look at the R squared? We'll just call some R squared variable. We'll model.score. It's just linreg.score. Or no, we can train model.score. Train model model.score. So we're just going to copy and paste the, really quick, just copy and paste the X and Y. And then first, and this will give us our R squared value, which is 0.39, which of two variables is actually really good. And we want to see how well it predicts. That is just another that's a really simple. So predict set. So we wanted, so 0.39, that's pretty good. That's not phenomenal, but it's solid for a really naive model. Naive meaning it has very small variables, it only has two variables. To predict something as complicated as what is the final score of an NFL game, which is subject to so many factors. This is really good. So what we're going to do from here is we want to predict it to see, okay, so we know it's fit that well. That just tells us how good the line is. It doesn't really tell us how off we are, because it might have this super low R squared, but we might be off by only like a point or two, which would be great. Oh, also a quick note. This is not a predictive model at the moment, because it's just looking at things that happen within the game. It doesn't look at what happens going into the game. It's just saying, given that this happened in the game, what is the probability that, given this happened in the game, what do we expect the final score to be? So predict set, what we're going to do is we're just going to do train model, predict, and we're going to do this on our test set. And with the same, but we're only going to look at the X. So home, EPA per play, and away EPA per play. Actually, let's just look at what this returns us first, so that we know what to do with it. So this just gives us an array of what it expects the final score for each game to be. So we can actually be really clever, and we can make this column in our test set. We'll call this a pred tote, so the predicted total. Okay, cool. So if we look at tests really quickly, so now we have the actual total and the predicted total. And we want to look at the residual, so the difference between the two. We can just define another column, resid. Can someone tell Joey that Josh is going to do that tomorrow because he was super busy today? I got that.
Yeah, I'll tell him.
Okay, thanks. Yeah, Josh told me today that he said he was really busy, and obviously this is not a super important thing that he gets the PFF subscription. Okay, so keep in mind the total minus the predicted total. So if we over predict the game, it will be negative, and if we under predict the game, the value will be positive. So here we can see we're really good with this 2019 Chiefs Vikings game. We were only off by 0.2 points, but then there were some not super great games, like this 2018 Ravens Saints. We over predicted by 12. So here we actually do some quick down and dirty looks at how we did. So we'll do test resid. So we can actually look at what our MAD is, our mean absolute residual. What that is that just looks at the app. So it sees how off we are in either, regardless of direction. Because we would expect that we just look at the mean of the residual, it would be 0. And it's at 0.3, that's essentially 0. And you would look at this at first and say, oh my, our model about to be really good, even though it only has 2 variables. When in reality, if we actually look at it, test.zid.hist, what we actually see is no, it's just roughly symmetric. And that's why we're getting that roughly 0 residual. It's not that we're actually really good. It's roughly symmetric. And it's actually does still have that slightly right-tailed shape, which is encouraging. But let's say instead, but let's do.
We sorry, I missed because I had to text Joey. But how did we get to the test resid? Oh, it's test total. Okay, thanks.
Here, I actually need to throw that in chat. So, and actually, a really encouraging thing about this is that we have. Oh wait, that's the test resid. That's not the. No, yeah, this one. So actually, really encouraging about this is it does still have that right tail. So it does still sometimes predict high-scoring games. But oh no, the residual is really high. We can actually look at the predicted score to see if it has that still. No, the predicted score does not predict 100-point games, which is fine, but it means it's greatly under predicting the finals, final totals. So here, let's look really quick. Oh, and yeah, so we can see that when we look at the residual. Yeah, we're under predicting that, not like the residuals. But we can get some hard numbers on this. We'll look at the MAD, the mean absolute residual. So test resid dot mean. I think we can do it like that. Yeah. So we're usually off by about 8 points, which is not great. Considering we're not even trying to predict the total, we're just looking at here's what happened in the game. What's the total? We're off by over a touchdown, which is not great. So, but that's sort of what we would expect with this. So cool. So we have training and testing sets. We have a trained model. So now we start to think, okay, well, what else could we put into this? We had that idea earlier, where we looked at the home and away EPA per player actually better correlated with the score of the home or away team rather than the total. So what if we tried to make 2 separate models and then see how that phased out? So let's actually try that real quick. This was planned. So here, we actually keep the same training and testing sets. So we'll bring this bad boy down here. Okay, so now, but what we want to do instead is we want to look at a, so home train. That's a fun thing. So what we want to do here is we want to look at the home EPA per play and use that to predict the home score. And we can do the same with away. I've used this technique before. I have for college football, I have like a predicted drive points model where you predict how many points a drive will score based on what happens in it. And I do this technique where you kind of chain together multiple models. I'm sure there are implications of this and why it's perhaps not best practice. But for a teaching sense, I feel this is fine. I'm just not a data science major, so I don't know if this is bad, how bad it is. And we can look at the home train R squared. Home train dot score. Score. Yeah, we just did. Yeah. Yeah, the train EP play score. And actually, we don't even need to call this anything. We can just do it. When regression, what do you mean it's not callable? Oh, with dot fit. Whoops. I forgot to call the function. Train model dot score. Did I do anything wrong? What is it? Why is it doing this? Not quite sure what I'm doing wrong here. I need to put another. Okay. Oh, yeah, because one of these needs to, I think, yeah. Yeah, so the reason we need these double brackets here. And by the way, this is a much better R squared than we had with the, we can check with the way. Really quick, why we need the square brackets. So for whatever reason in Python modeling, how do I clear? Whatever. So in Python modeling, there's this issue where you have to basically you have to make one a column and one a row. So the inputs have to be this sort of array, and the output has to be in this form. No, it's other way around. Reverse. So other way around. Inputs have to be like this. Outputs have to be out like this. Why? Linear algebra. Basically the way, because the way you do a model, and this is really just a bunch of matrix multiplication. An algorithm really is just multiplying a bunch of special matrices together. So you just have to specify one at the input as a row instead of a column. And the way you do that is you just have these double brackets. And so that's why we were getting that error. And if we look at away really quickly. Yeah, so the away score is actually a better fit with the home score. That might just because of our sample size and the random variation of that. But okay, this is really good. So now let's see. So now what we can do is now we can actually predict in the same way that we did before. So we look at the, so we're just going to copy and paste these bad boys. Home pred. Again, I'm copying and pasting a lot of code here, and it's not very pretty, but gets the job done. So yeah, now we can get the home predicted score and the away predicted score. We can say test home pred test away pred, and we can look at the residual as well. And there's almost certainly more efficient ways to do it. My middle name is not efficiency, it's Robert. Okay, so let's let this bad boy chug. Yeah, it'll yell at you. So I think Python usually yells at you when you do this, but you do like this thing right here. They usually yell at you. As you can see, we got yelled at a couple times for it, and they can deal. Okay, so now what do we see? So if we look at the individual home and away scores, we actually got two 1731s. So they seem to be a little off, and if we want to, we can actually we can run our analyses on those individually to see if they're better than what we expect for the total. For these purposes, that seems boring, and we have about 10 minutes left. So we're gonna skip that step and look at the total to really see if there's any improvements in that sense. So if you remember from earlier, our mean residual was about 8.6 points, if I remember correctly. And just from looking at the residuals here, doesn't look too much better. So not text, get that off my screen. So what we can do is we can do some quick visualizations. Quick visualizations are better in Python. I will concede. However, the more advanced stuff's not fun. Yeah, so we just want to make a quick histogram of this. So, okay, it's symmetrical, and we actually do hit a little bit closer to those upper limits. We are approaching 70 total points. Now, again, this is a simple model, so it shouldn't be too bad, but the residuals do look to be smaller overall. Now, it does underpredict still, but doesn't seem to be as bad about it. So now we look at, we're going to look at our MAD real quick. So abs, test, resid. So our MAD is about 9.6. So we are actually worse than if we just predicted the total as a whole, than if we predicted the home and away by themselves. Now, what explains this? Well, now let's go back and now let's look at the we'll look at the home and away resids, and we'll just define those really quick. So test home resid. We'll also look at test score. This test home pred, right? It's pred, it's home pred, not pred home. Home pred. Now we'll just copy and paste for away. We'll look at abs. We'll actually print this out so you don't have to run it multiple times. Print home mad equals resid mean. Okay, so to quickly explain what's going on here. So of course here we're just making the residuals as we do again. These print statements, I don't know if we ever talked about it, but an R to add. Basically what we're doing is we have one string, they're adding another string to it, and that's printing out a whole string for us. So we have, yeah, so we're just getting the mad and we're making that a string and then we're printing it out. So you don't have to run it multiple times. So what we see here is that our home MAD is about 5.4 points and our away MAD is about 4.7 points. So both under a touchdown, still both pretty big. But actually, this lends us to something really interesting, where maybe the reason, I'm almost certain the reason, that our total MAD was so high, is that our total MAD is really close to the sum of our home and away MAD. So one of the issues with perhaps doing what we were trying to do, noticing that it predicts either score better individually, is that the uncertainty that comes along with it adds together almost perfectly, so that we get more uncertainty in the total final variable that we're trying to predict. So that's why it's best practice to just predict the thing we're trying to predict. So yeah, that's a quick rundown. So what did we do? We talked about the SciKitLearn packages, how to test in the training and testing sets. We loaded in multiple data frame, loaded in multiple years of data, created some conditional statistics, merged them together, some summary statistics by looking at the last value in a group. We created something that is a linear combination, merged it together, did some EDA, some exploratory data analysis, split into training testing sets, ran a naive model on our target variable, and then we noticed, using something we noticed in our EDA, try to make two separate models and add those together, realizing that doesn't work as well, as the uncertainty inherent in either actually manifests it in both. We also took a breath to explore our model via some more EDA. So yeah, that's kind of the quick rundown. If you guys have any questions or do want to look at something really quick in 5 minutes, go for it. And I think I went through that pretty fast, but I think it was thorough. Oh, and reminder that these are so we're trying to predict the total of the game using data in the game. So it's not predictive or anything. This is really just a learning exercise. Oh, and this is also, I have a post-game win probability model for college football games. And this is more or less how I did it, just with a logistic regression instead. You can actually take a peek at that if you want, just for fun. Is it? Yeah, it's right here. Just take some stuff, split it up. Oh, that's because there's some not full games. And we filter overtime games because we don't have that data. And then we just do a quick regression. So yeah, with simple models, this is why R is better. Just because this is really one, while in here this linear regression took us 2 lines. Well, yeah, same idea, but personal preference is R for me. So yeah, that's that. If anyone has any questions, comments, concerns, worries, otherwise we should be pretty good to go. So anything?
It was really good. Thanks for doing that.
Yeah, no problem.